Welcome, ladies and gentlemen. Today we're going to use Geogebra to help us make an interactive drawing that'll help us examine how light behaves within a raindrop in the atmosphere. Hopefully, by the end of it, we'll have a nice interactive drawing that'll help us deal with Snell's Law and show us exactly how light is behaving inside of a raindrop and ultimately tell us how a rainbow is formed. Before we get to the actual drawing, I want to have up at the top of my list of things over here in my algebra bar, I want to have a list of the refractive indices that we're dealing with. So in a raindrop, we have air and we have water. The only complication is that the refractive index for red light and blue light are different, at least when they're in water. So I need to create 3 sliders total, one for the refractive index of air and one each for the refractive index of red light through water and blue light through water. So to create the sliders, I just have to define a new variable in Geogebra. And there's a really cool thing that you can do is you can do an underscore to create a subscript. So I'd like to start off with the n value for air. So I'm going to type in lowercase n underscore, which gives me the subscript, and then I can type air. Now Geogebra doesn't know what that is, so when you hit enter, it's going to say, hey, do you want to create sliders for that? And you're going to say yes. Yes, I do. I'm going to continue doing n with an underscore of in water, water, let's try that again, dot red light. So this will be my n value for red, and I say yes, I do want to create that slider. And finally, I'm going to do n underscore water dot blue for the n value of blue light through water. Now, the standard default settings for a slider in Geogebra is that it runs from -5 to 5, I believe, by tenths. We need to change that over here in options. So you need to change the, you have to have that point selected. And then in options under the slider tab, we're going to run this from 1, which is the index of refraction in air, all the way up to 2.5, which is way more than we need because the index of refraction in water is 1.331 or something like that. But you'll see why we want to crank that all the way up there. And we do want a very fine increment on this, so I'm going to go to the thousandths on that. So you should do that to all 3 of your sliders. I'm going to do that and return to you. Now that I've got my n value sliders, I can go ahead and move on with the actual drawing. So when raindrops are sufficiently small, the surface tension of water will create a nearly perfect sphere. So what we're going to do is we're going to make a drawing of a cross section of a raindrop. So that means I'm going to draw a circle, basically. Long-winded way to say I'm going to draw a circle. Like that. And the second thing that I'm going to do is I'm going to use a segment to represent an incoming light ray. Okay? Now, this drawing gets really messy with a lot of labels really quickly, so you can right-click on any object and just say, okay, I don't care what that line is named, I also don't care what the circle is named, and you can deselect the labels. I would suggest doing that. I'm going to play around with the formatting here. I'm going to make the points a little bit smaller so that my drawing looks a little bit nicer for you. I'll be back in a second. So now that I've cleaned that up, I can now use the Selector Tool and I can see what I'm doing. I can use this to change the angle of the incoming light ray. I can pull on this button to make the incident intersection point different or change the radius of the circle, and this will change the location of the center of the circle as I drag it about. So this is our setup of our initial problem. So now we're going to start applying Snell's Law. And in order to apply Snell's Law, we need to know a few things. We need our n values, which we already have. You can see that I've actually set it to the appropriate value. That's 1.331 and 1.340. The second thing we're going to need is a tangent line. Well, we're going to need a normal line because every calculation that you do with Snell's Law is always in reference to a normal line. A normal line is a line that sticks directly perpendicular out of the surface. And in this case, we're dealing with a curved surface. So if we run for instance, one of the properties that we learned about in geometry this year was if we run a radius, that line will be perfectly perpendicular to the surface of the circle. So in this example, it's very easy just to create a perpendicular normal line right away. I'll show you a separate way to do that. If you're dealing with some random curve, Geogebra has this feature in here called tangents. You can create a tangent line to any curve or function that you define, and what you do is you simply select the point that you want the tangent line through and the curve, and it will create this tangent line. Now if we wanted the perpendicular line to that, then we would just say, hey, let's create a perpendicular line, and it always gives you directions down here at the bottom of the screen. and we would need to know the line that we want to be perpendicular to and the point through which it would like to go. So what I'm going to do here is I'm going to set up a normal line here so that we can get ourselves going. I'm going to format it so it's a little easier to see. So here we go. We have a dashed line representing the normal line to the surface. And now what I need to know is I need to know the angle of incidence before I can go ahead and figure out the angle of refraction coming out of this intersection right here. So what I need to do is I need to measure this angle right in here. And to do that in Geogebra, I'm going to need a second point right there so that I can measure the angle using this tool by selecting these 3 points in the appropriate order. Now if I had done that C to this point to D, it would actually measure the larger angle, and I wanted a smaller one. So the second thing I'm going to do is I am going to rename this angle, and I can do that by selecting it, going over to Object Properties, and I'm going to name this Theta 1 and hit Enter. And you can see that it gives a subscript with that underscore thing, and you can also change this formatting just to show the name of it, and that's really all we're concerned about. We'll let Geogebra worry about the number, but since we're going to deal with a lot of different angles in this problem, it's nice to label them so that we know which is which. And once I define Theta 1, you can see that it reads it out here in the algebra bar, and it also gives a value for it, and it's all still interactive. So if I change that, it changes the number. If I change any of the locations of any of the points, it also goes to match. So now I have Theta 1. Now I'm going to apply Snell's Law, and if you don't recall, this is Snell's Law right here. And we are curious about Theta 2, the outgoing angle, or the angle of refraction in reference to the normal line. So we need to solve that equation for Theta 2. You can do that by doing a little cross products and then applying an inverse trig function. Now, what we have to do specifically in Geogebra is we need to apply that trig function. It's a little weird. You got to say a sine x, which stands for arc sine. It's an old way of saying inverse sine. But once we type that in, it'll calculate that angle for us. So we're going to go back to Geogebra, and we're going to type in a command in the algebra bar that will calculate that angle for us. So to calculate Theta 2, we're going to define it first off. So I'm going to start by typing in basically the command that you see on your screen right now, which is Theta underscore 2. All right. And we're going to say that Theta 2 is equal to arc sine. I'm going to throw in a set of parentheses here. Then I'm going to do the n value for air. That's our incoming ray. And then I'm going to multiply that by our value for, or times sine of Theta 1, and I can just type in Theta 1 as we've already defined it, and it knows what that is, and then we finally divide by N2, which in this case is the N value for water, and I'm going to do red light first, so I'm going to go N underscore water dot red, and Geogebra knows what all those things are. And once I hit enter, you can see that it calculates the angle of Theta 2. And it says 0.53. That's a different measuring standard than maybe you're used to. It's not degrees, it's radians. So that is a reasonable answer. Now that we have Theta 2 calculated, we actually need to draw an angle of that size. So to do that, we're going to put a point on this radius here, and we're going to rotate this point Theta 2 degrees in this direction, so from the normal again. To do that, we are going to use this tool, which says create an angle with a given size. So we're going to do that, and you have to select the point, then the vertex, and then it's going to say how far do you want to rotate it. Well, we want to rotate it, and we're going to be defining this under Theta 2 because we want the whole drawing to remain interactive. So I don't want to punch in 0.53. I'm going to type in Theta underscore 2. And I'm going to delete that 45, of course. And then it says, which way do you want to rotate it? So we're going to rotate it counterclockwise off of that normal line. Once I hit OK, you can see that E has become E prime, and now I can connect that point with a ray. Now, that ray will come over and it will intersect with the side of the raindrop, which is a very interesting point to us. So we are going to calculate or construct an intersection here between the circle and that ray, and a point should pop up right at that intersection. Now at this point we have a couple options. We could continue to trace this light ray as it goes out of the raindrop, or we could consider the reflection off of this. So we could bounce it off and it'll come back this way. Since we're talking about a rainbow, and since in real life an observer would be somewhere over here and the sun would be up here, we want to consider that reflection on the inside surface of the raindrop and see what happens there. So there is going to be a refraction right here that happens, but we're going to concern ourselves with the reflection inside of the raindrop before that point. So what I'm going to do is I'm going to draw a segment over the top of this dashed line here, and I'm going to turn that red, or in this case slightly pink, and that will represent our, basically, once it refracts right there, it's going to split into red and blue, so now we have it split into red. And then the whole process starts over again. So we're going to draw another ray from the center to there, and then we can calculate another theta right here. In this case, it's a theta of reflection, so we're just going to duplicate this angle right over here. And then we're going to deal with refraction down here again. So with reflection, we're just going to try to duplicate this angle. Before I continue, I'm going to clean up the drawing, hide some labels, and just so the drawing looks nicer. Okay, now that the drawing is cleaned up and we can see things a little bit more clearly, now is a good time to check to see whether it's actually still interactive or not. And you can see that by changing the angle of incidence right there, everything reacts according to Snell's law. And if you change, say, the indices of refraction, you get more or less refraction as you crank those values up or down. So the next job is then to reflect this point over here, basically recreating this angle. Now it wouldn't be too much of a stretch of your imagination, and you could definitely prove it through geometry that this angle right here is this angle right here, and we're going to try to replicate it yet again right there. So what I'm going to do is I'm going to rotate this point right here about this vertex right there by theta 2. So I'm going to create an angle with a given size. I'm going to select my point that I want to rotate, my vertex to go around it, and then I'm going to name the angle by which it should rotate. So theta _ 2. And again, counterclockwise on this one. So you can see that it rotated that point down, and I can create a ray going through that point, and all of a sudden I've got this other intersection, and look, we're pointed down at the observer now. That would be, down on the ground looking at hopefully a rainbow. So I want to find the intersection point of the circle there. To do that, just highlight both things with that intersect tool, and that will be guaranteed to be there. I'm also going to draw a red segment or a pink segment right over the top of that ray so that I can later then delete the ray. Again, we're going to create another normal line to the surface so that we can perform Snell's law again right here. So we're going to do an angle of incidence right there, which, surprise, surprise, it's theta 2 again. And then we're going to calculate the outgoing angle as a final step. Let me clean up the drawing and I'll be right back with you. Okay, now that the drawing is cleaned up again, our next job is to calculate the outgoing angle right here based on this incoming angle right here. You do a little geometry, and again, theta 2, theta 2, theta 2, and this is again theta 2. So our incoming angle is theta 2, the same angle that was calculated up there. It's just been replicated 3 times in a row. So next up we need to figure out this angle right here, and this one will be different than theta 2, so we're going to call it theta 3, our final angle, and we're going to define it using the code on the screen here as we type it in. So I'm going to say theta 3 is equal to arc sine, and now we're going from water to air, so I need my n1 value is from water, so I'm going to go n_water.red, and I'm going to multiply that by the sine of theta 2, so theta _2, and then we are going to divide that by the n value for air, which is 1, so you don't even have to type in divide by 1, but since we want to make our drawing interactive, I'm going to type in n for air, and that will be our theta 3. So theta 3 has been defined and calculated as 1.05, and that's in radians, not degrees. So again, it is a reasonable answer. And now, finally, we're going to plot an angle rotated from our normal line right here, so I'm going to need a point there. And I'm going to rotate that, this time clockwise, from the normal line by a measure of theta 3. So I'm going to select the point that I want to rotate, the vertex, and this time I'm going to type in theta 3. And the other thing I need to change is that we are going clockwise this time. And there we go. I'm going to connect it with a ray, and I'm going to turn that ray pink because that represents our outgoing red ray. And we'll make it solid. Just like that. And now we have a completely interactive drawing tracing a red or a white line, or incoming white light refracting into, or at least tracking the red light that's within that white light through a raindrop. Okay, so now if we want to talk about rainbows, then we got to talk about blue. So we're basically going to repeat this exact same process for blue. I'm not going to do that on video. It's basically the same thing. But I'll tell you, on this first refraction right here, I'll show you an intermediate step there. The whole reason we created sliders is because the index of refraction between red light and blue light in water is 0.01. It's 1.331 versus 1.340. So when you get down to actually drawing it on the drawing, the two rays, the red and the blue, run into each other. And by creating sliders, you can create more separation and just basically give yourself more room to work on the drawing. I will run the first refraction here and I will show you exactly what I mean in just a moment. Okay, so here's what I'm talking about. I've done the first refraction, but using the N value for blue light now, and you can see how close these are. So it's really difficult to figure out where the intersection is. But if I change, using my slider, the refraction index, now I can get some separation here and I can clearly see that the intersection right here is over here, and I can calculate, or I can construct it more reliably. So that's the whole purpose of the sliders, is just so you can create a little separation, and in the end product it'll make our drawing look a little bit better too. Now I'm going to go ahead and complete the drawing, and I'll meet up with you in a moment. Okay, so going through that whole process again and tracing the blue light through the raindrop, you can see that this is our final product, and of course I've cleaned it up so it looks nice. But now you can see that the drawing is still totally interactive. If I change that initial angle of incidence or the size and location of the raindrop, everything reacts accordingly. And you can see just barely that the blue light refracts a little bit more, and then it crosses over the red light, and so that the blue light is coming out on top of the red light right there, creating a spectrum right here, or a rainbow, for the observer. Okay, so we have separation of light, but how does that create a rainbow for the viewer? And you might notice that blue is on top, and when you look at a rainbow, a single rainbow, you get red on top. So why are the colors reversed, and how do I get a rainbow if for any incidence angle it looks like both colors are being reflected back at the observer? Well, there's a slight little hitch in its step right here. As I increase theta 1, you'll see that there is a maximum angle of refraction, or there's a maximum angle of viewing right there. So it kind of goes in, it has that, it kind of bounces back from a number. We can see that a little bit better if I put a trace on these things. So if I show a trace and I show a trace, you'll see what happens is that while yes, all colors of light are reflected back towards the observer, if we look at it, there's a special part where there's only red being reflected back towards the observer, and then the subsequent colors would follow until you get to blue, and then it's just a hodgepodge mix of everything. So when you look at a rainbow, you'll see red going to blue, and then you'll see a hodgepodge of all the colors. Well, what is that? It's white. So if you look at the inside of a rainbow, you'll notice that it's brighter than the outside of the rainbow. But then the question is how does the color work? Because remember, as you observe a rainbow, it goes from red down through violet, whereas this is showing that violet is up on top. So the color order seems to be reversed from what you would expect. So I have another drawing to show you that explains that. So we just performed a few calculations to show this is exactly what happens in a raindrop. But we have to remember that there are millions and millions of tiny little droplets in any given rainstorm. So you have this arrangement right here. So at any point that you look up at the sky, you could be seeing the reflections from literally millions of raindrops. So how is it that we invert this color order between blue and red? Well, it's helpful to think if you just look at one raindrop in particular. So right here, here's a raindrop. It's high in the sky, and it is reflecting all the light here Specifically, this is the part that's only red, this is the part that's only orange, and so on until you get only blue. And then in the middle here, again, all light colors are being reflected, so it's very bright right in here. So right now, the position of the raindrop is such that it's overshooting the observer's head. As the observer looks lower in the sky, though, as I drop that, you'll see that the red light hits the observer's eyes. So that means that when a raindrop is this high in the sky, the observer will see red. And as I continue to drop this until the blue line, you'll see that now the drop that is showing off the light, that is reflecting the light, is lower in the sky, so he would see red on top of blue. So this is generally the way it goes with more than one drop, is that you have some that are reflecting and you don't see anything. You see some that are reflecting and seeing red, and then you've got a million in between that are orange, yellow, green, blue, all the way down to violet, ideally. So here's a picture of an actual rainbow, and you can see that this is happening. So we've got red to blue and violet. You can also see that inside of the rainbow it's much, much brighter because all of the colors are being reflected, not just a single color like on the edge of that spectrum. Here's another picture that shows the same deal, very bright compared to the rest of the sky. And then you'll notice that some of these are also double rainbows, and yeah, double rainbows are totally possible. It just does a little bit different reflection. So, but you look up at the double rainbow and you notice, hey, those colors are inverted the way maybe we could have expected from the first drawing. Well, this is what's happening for the secondary bow. You'll also notice that it's fainter, and that's because it has to do one more reflection within the droplet. So it comes in from the sun at the bottom of the drop, reflects and refracts and yada 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 down to the observer. And this time we have reflecting red on top and blue on bottom, which then by the observer would be inverted again and getting you this color spectrum from violet to red. You can actually, even in this picture, see a slightly brighter outside of the double rainbow and then dark and then really bright in this picture. That's why I like that one. So that's how a rainbow works. I hope you enjoyed this video.